Okay, today we are going to talk about connecting our PIC10F200 to our computer via a UART, or Universal Asynchronous Receiver Transmitter, between the two of these and basically figure it out. I think right now we're going to be focusing quite a bit on what UART is in general and that communications protocol, but of course we'll also go through how we program the PIC10F200 in assembly to actually execute it. Now the PIC10F200 does not have a UART hardware portion in it, so it is all going to be bit banging, and it's all going to be done in software, which is going to be lots of fun, really exciting. So we have my computer that's hooked up with a USB to serial converter, and then this serial converter goes to an RS-232 converter, which takes that serial communications and changes it to the same voltage levels that you would expect from the UART. Because really, serial communications and RS-232 communications and UART use the same protocol. They're just at different voltages, and there are some other minor differences as well. One of the things that you might notice is that this is a DB9 connector, and so that means there's 9 pins, whereas we're only going to be worrying about basically 2 or 3 things, and that's ground, connecting it, and then receive, transmit, and that's really all we need to worry about. The rest of the other 6 pins are just hardware control and some sort of stuff to make sure that everything's working great, which for us, we don't care about. So again, we just got this Spark Fun thing that bought years and years ago. I'm sure they're still selling this or something like it. And then I also bought this USB to serial thing years and years ago. I don't remember what it is. Sergey has in the written tutorials his recommendations and what he used for the written tutorial, but for us, this is all we're using. So let's get into what a UART, or Universal Asynchronous Receiver Transmitter, actually is. Now, universal just means universal, like you're going from a microcontroller and actually are able to talk to a computer. So I'm assuming that's what the universal talks about, or what it means. The asynchronous is different though. Notice how we only have the receive and transmit. That means that there's not a line that is providing a clock, because that clock would synchronize everything. And the way this works, and the way it works asynchronously, is that you say, in this case particularly, we want to communicate at 9600 baud, and you make sure your computer's set up to receive and transmit at that speed, and make sure your microcontroller is set up, and then once either one sends a start bit, after that it just waits a certain amount of time and says, okay, it's been a certain amount of time, measure, measure, measure. And so if you have any differences in the baud rate, it's not going to work, because one's going to be saying, hey, you should be measuring every, I don't know, 20 microseconds, and the other one says, okay, I'm measuring every 30 microseconds, so you're going to be off. With that, let's look really quick on what a UART waveform looks like. Now, it is a active low, so your voltage is typically high, and when you're actually sending a signal, it drops down. So the first start bit, the thing that says, hey, I'm about to send some information and let's start our internal asynchronous clock, it drops down. So on the receiving end, it says, hey, something just dropped. Let's wait a predetermined amount of time and then take a sample. Is this a 1 or a 0? And then wait a predetermined amount of time. 1 or a 0, 1 or a 0, 1 or a 0. And most of these packets are 8 bits. So you have 1 bit to say start, you have 8 bits of information, and then 1 bit that says stop, and that's the end of the packet. And that's really it. UART, I've heard other people say that it's difficult. That's never been the case for me. I've always found UARTs and this form of communication to be very, very straightforward, because you don't have to have that clock. You can just set the baud. It's fast enough for sending little packets of data, and it's just great. So I don't know. Other people may disagree with me, but I think UART is very straightforward. Okay, with that out of the way, let's look at this again really quick. You'll notice that it's not just the communications equipment. We have a switch on here, or a button, excuse me, and then we have an LED. And what we're doing here is, I'm going to use the button, so when we press the button, it will send a message to the computer, basically just saying hello. And then on the other side, I can send a 1 or a 0 to turn the LED off and on. So we're going to show that we can go both ways on this. So that is the hardware we have set up here, and if you want to see that schematic, you can just go to circuitbread.com and look in the tutorial, because we'll have all of this stuff up there. Actually, it is already up there, so you can just go and look at that. One final word of warning, and I think perhaps the most confusing thing with not only a UART, but any communications, is receive and transmit go opposite. So one is transmitting, one is receiving, the other one is receiving, the other one's transmitting. So you got to make sure that you're not hooking transmit up to transmit, receive to receive, because if you do, it's not going to work and it's going to be terrible. Actually, I'm totally kidding. There's not going to be any problems. It's just not going to work. And one of the first things, if after setting something up, it doesn't work, you're not sure, you can just swap them. And if that still doesn't fix it, I'd swap it back. It's not going to hurt anything, but that is the most common thing that that I've seen people just, oh, which one? And it gets even more confusing once you have this in here, like, oh, is that the receive? Is that where I'm supposed to be hooking the receive up for the microcontroller? I don't know. Don't worry about it. Take your time. And even if you get it wrong, it's not going to break anything. You can just swap it and try it again. So with that, let's move on to the hardware. By that I mean software. Okay. Now in the software, we have our initial, everything is normal on the first 15 lines. We don't even need to worry about it. I will say one thing, that in line 16, we set GP2 as high, and GP2 is our transmit. So our microcontroller is transmitting from that. And since, again, active low, we want it to be high when it's just idle. So that is what we're doing here in 16, is we're setting GP2 as output high. Now, the rest of it, we have a loop from lines 17 to 44. And this loop is going through and just, one, checking to see if the button is pushed, and two, checking to see if we've received a command from the computer. And we'll get into the details there, but past that, we only have two other sections. We have 46 through 66, which is our subroutine that transmits data from the microcontroller. And then we have our subroutine, our receive byte from 68 to 93, which is how our microcontroller receives data from the computer. Everything from 94 and below, I'm not even going to worry about at this moment because it's all delays, and we've talked about delays in several other previous tutorials. If you're still confused about those, go back and check those out. So let's go back and look at our loop. So this is our main function, and from this main function, we call the transmit byte and the receive byte subroutines. So in number 18, we have our bit test file skip if clear. And so basically we're checking GP3, which is the button that we have right here, and it's checking to see, hey, has anybody touched the button? If it has been pushed, then you skip 19. Otherwise, if it's not been pushed, it jumps from line 19 to go to wait receive, which is down in 41. And at that point, it checks to see if we've received any messages from the computer. So let's imagine that we have pushed the button. So in line 18, we skip down to 20, and we do our debounce delay. Say, hey, did that actually happen? Was that a real thing? And once it goes through and we've verified that we've actually gotten a message going through all of those debounces until line 26, once it's 26, the microcontroller says, hey, I know I got something, so I'm gonna send the message through the UART. And so each one of these lines is basically saying, okay, we want to transmit the H, so we're gonna move that literal into the working register, and then the call transmit bytes. So call transmit byte then, which we'll get into a little bit later, then transmits what is in the working register, and then we go through. If you look through, it's HELLO, and then basically two commands in ASCII code that say, give us a new line. So you'll also note that we have H in single quotes, and by doing that, instead of sending an H, the compiler knows to take that H and send the ASCII equivalent of the H, which I don't know off the top of my head, but whatever that is, it's sending that. And so both the microcontroller and the computer, when it receives an ASCII code, it knows, oh, hey, that's a capital H, and then that's a lowercase e. Oh, that's a lowercase l. And so using those single quotes makes it so you don't have to look at the ASCII table, and saves a lot of time, and it's fantastic. So that is basically it for sending the message, and we'll get into the transmit byte subroutine more in just a second, but it's pretty straightforward. Whereas the wait receive just goes and checks to see if the GP1 level is set or skipped, and GP1 is the receiving pin that is checking to see if we're getting any messages from the computer. So if it does get a computer, it calls the receive byte subroutine. Otherwise, it goes to the goto loop and jumps back up to line 17. So that's the basic overarching structure of the subroutine. Basically, check to see if the button's been pushed. If it hasn't, check to see if it's received a message. If it hasn't, start that over again. If the button has been pushed, send the message. If it has been pushed, the first thing it does as soon as it sends that message to the computer is then check to see if the computer sent anything back. And so that's basically it. So now let's jump into the transmit and the receive byte. So line 46 in transmit byte, and remember, a byte is 8 bits, so we are sending one 8-bit byte, which is the length of an ASCII code. So here we take the information that was in the working register and we put it into the transmit data register. We clear the count because we're going to have to send each individual bit by itself, and so we need to count how many bits we've already sent. So we clear that count, we then take GP2 and we drop it down. As I mentioned, that is the signal, like, ooh, okay, we're about to get something. So it drops it down and then it calls the UART delay. Because again, we are going to do this at 9600 baud, and that's slower than our microcontroller can think. So it says, okay, drop it down, sit around for a little bit, and then go to the next thing, sit around a little bit. So that's why we need all of these delays. So once we've finished with that delay, we then go to starting to shift the data byte. And so the thing we do first is we see if the bit we're looking at is a 0 or a 1. And using the BTFSC, so if it's a 0, then we skip line 53. And if it's 1, then we have a go to setting the bit. So all we're doing at this point is saying, is this a 1 or a 0? And depending on what it is, then we either set the output as a high or a low. And then once we go through that, we're now on line 58 where we are delaying. We have that delay. We take that data that we have in there and we shift it by 1 bit, increment the count register, check to make sure that the count hasn't already hit 8, because if we've already done 8, then we're done. And if we haven't already done 8, then we start this internal process over again, send the next bit, shift, check, send the next bit, shift, and then keep on going. And then once it's all done in line 66, we return literal to W, and we jump out of the subroutine and go back into the main loop. And so that's really it, is all we're doing in 46 through 66 is looking at that 8 bits, taking a sample, shifting, taking a sample, shifting, taking a sample, and making sure that we're pausing in there enough time that it is matching up the timing of what the computer is expecting when it is receiving that sample. So let's jump into the receive byte really quick, and then we'll be done with all of this. We'll do a demo really quick and we'll be done with this, and you will feel so much smarter. So the receive byte is basically the opposite of the transmit byte, but there is one important thing I'd like to point out. In 69, there is the call half UART delay, and that is simply something where if we notice that we are getting the start bit from the computer, we want to wait just a little bit so that we are taking samples in the middle of the cycle and not on the edges. Because if we're on the edges, then it's more likely that we might, if we're a little bit too fast, we're going to get the previous data. If we're a little bit too slow, we're going to get the next data, something along those lines. So we want to have that delay to put us right in the middle. But other than that, it's the same concept, and all you're basically doing is taking the data as it comes in and saying, okay, put the first piece of data there, shift, put the second piece of data there, shift, put it there. And each time you're doing that, you're checking the count to make sure that you haven't run out and then you're out of space and you're not sampling the right thing anymore. And that's really it. So I'm not going to get into detail on the receive byte because it's just the transmit byte in reverse with that delay is something that you should worry about. So with that, let's take this program, download it, put it on here, and I'm going to show it to you in operation. Okay, now we have it set up. So on here, since I'm using a Mac, I'm used to the Windows machines where I used Hyperterminal or whatever. But on Mac, there's this pretty cool program. It's called Serial. I've only used it to do this, and so I don't have a whole lot of experience with it. But I love just how quick it was. Just plugged it in, and it just worked. So as you can see on the screen capture right here, there is the window where I should be receiving data and the window where I can send data. So let me press this button here and see what pops up. Oh, it just popped up hello. So you see how it popped up, said hello, and now it's on a new line. So if I push hello again, it's doing it a lot. And then down here, I can type a 1 to turn it on and a 0 to turn the LED off. So let me put the 1 in, press enter. Now the LED is on. Now let me put a 0. Now the LED is off. So you can see communication both ways, receiver, transmitter. That's pretty simple, but at the same time, you can get really powerful and make very interesting interfaces where you can get a lot of good, easily readable data from your microcontroller. And I remember the first time I was able to get my UART to communicate with my computer, I felt like top of the world. I think it's 11:30 at night and my kids were asleep and I was jumping around super happy because I'd been banging my head on it because I didn't know Sergey at the time, so he couldn't help me figure stuff out. It's just a wonderful feeling to be able to see actual, hey, I did this and it's showing up here, and hey, I'm doing this and it's going over there. Maybe I'm just crazy. It's entirely possible. But I hope that was a good overview of what the UART is, and also how to bitbang or create your own software UART interface and can communicate between your microcontroller, the PIC10F200 specifically, and your computer. If you enjoyed this video, give it a like, subscribe to our channel, and we will catch you in the next one.